Okay, so now we get to a very important part of our course. This is going to give us incredible predictive power, and it's probably going to seem a little obscure if you haven't seen it before. So we're going to talk about Lewis symbols and Lewis structures. I'll tell you why it's important. It's important because chemistry is the study of materials. Moreover, it's 3D in nature, right? So it's shapes. Materials interact with other materials in shapes and charges. So consequently, this Lewis symbols are going to help us appreciate shapes. All right, that's what this is all about. So, all right, let's get to it. All bonds involving the transfer of all bonds involve the sharing or transfer of valence electrons between atoms. So we've used this term before, valence. We've used that term before. What does it mean? Valence electrons are the electrons in the outer shell. Okay, valence are the electrons in the outer shell. So a Lewis symbol now consists of an elemental symbol surrounded by one dot for each of its valence electrons. So what is the outer shell of boron? Here is the outer shell, right? So it looks like there's 3 electrons in boron's outer shell. So boron's valence or Lewis symbol is going to be 1, 2, 3. Can you see the 2 shell is carbon's outer shell? Carbon's got 4 then. 1, 2, 3, 4, right? Carbon's going to be 1, 2, 3, 4. That's a symbol for carbon. The Lewis symbol for nitrogen, we look at nitrogen's outer shell is 2, right? And it's got 5. Can you see 2 plus 3 is 5? 1, 2, 3, 4, 5. Okay? So that's how we draw the Lewis symbol for atoms. So here's some examples. The electronic configuration for sodium is, with the condensed one is neon plus 3s1, so there's going to be 1 electron in its outer shell. Magnesium is 3s2. There are 2 electrons in its outer shell. Aluminum, right? Can you see that? 3 electrons in its outer shell, and so on. All right? So Lewis symbols illustrating the number of valence electrons are shown here. These are in the 3rd period of the periodic table, and I think that might be a good introduction. More practice is probably going to be necessary. So let's talk about the Lewis symbol of ions. Cations are formed when atoms lose electrons, right, represented by fewer Lewis dots, whereas anions are formed by gaining electrons. The total number of electrons does not change, of course. So an ionic bond forms between sodium and chlorine when this electron, right, can you see that, gets transferred over to chlorine and becomes a chloride ion, right, and a sodium cation, and so consequently they're attracted to each other by electrostatic charges. Lewis structures now are drawings that use Lewis symbols to describe the bonding in molecules in polyatomic ions. We're going to work with compounds containing only main group elements, so we're going to keep things pretty simple. Well, it's still going to be complicated, right? But simple as we can, right? Lewis structures show the arrangement of all valence electrons in a covalent compound. So let's look at one. In the Lewis structure of a molecule or polyatomic ion, valence electrons ordinarily occur in pairs, right? So that's what we're going to be thinking about, these in terms of pairs. Keep our electrons together. A pair of shared electrons between 2 atoms is a bond. A pair of shared electrons is a bond, and is shown as a straight line connecting atoms. An unshared pair or lone pair of electrons is shown as a pair of dots on an atom. All right, noble gases, except for helium, have 8 valence electrons. So a noble gas might be krypton, right? And we're going to go 1, 2, 3, 4, 5, 6, 7, 8. And now let's appreciate the octet rule. The octet rule says this: that nonmetals, except for hydrogen, form molecules whereby sharing electrons allow them to be surrounded by 8 valence electrons, and therefore isoelectronic with a noble gas. They are isoelectronic with a noble gas, right? You see how this noble gas has got 8 valence electrons, right? So it's very comfortable. It doesn't want to make any bonds with anybody because it's got 8 electrons. Hydrogen is an octet rule exception because its outer shell only has a capacity for 2 electrons, and so we might, say it has a duet of electrons. All right, so let's look at some examples of Lewis structures. Water looks like this. Water's got 2 electrons here, that's a bond. 2 more electrons here, that's another bond. Here's a lone pair, and here's a lone pair. So oxygen now, in its valence shell, feels 8 electrons, right? Which is awesome. Everybody wants to have 8 electrons. That's what the octet rule is about. Hydrogen only has 2, which is actually good because its outer shell only has a capacity for 2. So that's good, right? Hydrogen has 2. Hydrogen has 2. Nitrogen has 8 electrons, right? Can you see how that's good? So these are good valence. These are good Lewis structures. Notice, by the way, for ions, we typically will put a bracket around the whole ion and put a charge on the outside, a bracket around the whole ion, and a charge on the outside, which we'll describe later why we're doing that. More examples of Lewis structures go here. Ethylene or ethene, depending on how you want to call it, right? See, look at those. There, that carbon's got 4 electrons. Remember, each bond is 2 electrons that are shared. 2 shared electrons, 2 shared electrons, right? So that carbon feels 8 electrons in its outer shell. This one also feels 8 in its outer shell. Hydrogen feels 2 in its outer shell, which is awesome. Good, love it. This carbon feels 8 in its outer shell, love it. This carbon feels 8 in its outer shell. Oops. Right? Important not to misdraw those circles if you're counting, right? 2 in its outer shell, that's good. Right, so acetylene also has all of its octets filled. Now let's look at some rules for writing Lewis structures. These are great rules. Determine the number of total valence electrons of the system. So for cations, we're going to subtract an electron for each positive charge. For anion, we're going to add an electron for each positive charge. Determine the total number of valence electrons. I will demonstrate this in just a moment. Number 2, draw a skeleton structure of the molecular ion. We're going to generally put the least electronegative element in the middle, right? And oftentimes there's only one central atom. There's only one central atom, and it's written first in the formula. Okay? So, you know what I'm going to say here? Guess. You're going to find that your guesses are typically right. But if you have a problem drawing the Lewis structure, we might circle back around and go, oh, you didn't put the least electronegative element in the middle. Okay, so step 1, determine the total number of valence electrons of all the atoms. Number 2, draw a skeleton structure of the molecular ion. Use single bonds to attach the terminal ions to a central atom. Okay, number 3, distribute the remaining electrons as lone pairs on the terminal atoms, except hydrogen, completing an octet around each atom. This is interesting. Number 4, if electrons remain, then place on the central atom. And then finally, we just go through and we make sure everything's got an octet. All right, so let's do an example. I'm going to come over here, open up my whiteboard. Let's do an example. Let's say H2O. Okay, so H2O. There's 2 hydrogens plus an oxygen, and each hydrogen has got 1 valence electron, and oxygen's got 6 valence electrons because it's in group 6. There's going to be 8 electrons total. VE is equal to 8. 8 valence electrons, right? Remember, it's only the valence electrons that we're concerned about. Another way to think of it is this. 1, 2, 3, 4, 5, and 6, right? Now, then step 2 is to draw the skeletal structures, which I kind of have here, right? And take 2 electrons and make a bond. 2 electrons and make a bond, okay? Oh, by the way, I've drawn all my 8 electrons. So step 3 was to add all the extra electrons to the terminal atoms. Here's a terminal atom and here's a terminal atom. But we're basically done with water. That's it. That's it for water. So let's do another example. It's going to be a little bit, let's say CO2, carbon dioxide. Okay? We're going to put the most electronegative element in the middle. The least electronegative element in the middle, right? Carbon. So this is in group 6, this is in group 6, and this is in group 4. So if we add all those up, it looks like we're going to have 16 electrons. Right, so let's go back over here. Step 1, determine the total number of valence electrons, which I just did in red. Number 2, draw a skeletal structure, which I did. Here's my skeletal structure. But use single bonds to attach terminal atoms to the electron, okay? So there's a single bond and there's a single bond, because these are terminal atoms. They're on the termini, they're on the ends, right? So I just drew up 4 electrons. I've got 12 to go. Now it says add all the, put all the extra electrons on the terminal atoms to make sure they have filled octets. Okay? So I've drawn all the valence electrons on there now. That was step 3, distribute the remaining electrons as lone pairs, completing the octet. Now 4, if any electrons remain, place in the central atom. There are none extra. Now number 5, if an atom does not have an octet at this point, then rearrange the lone pairs on the terminal atoms to make multiple bonds with the central atom until its octet is expanded. So this carbon does not have its octet. So I'm going to get rid of these two and redraw them here. Now carbon's got 6. That's awesome, but it's not enough. Let's redraw those. Aha. Oxygen, 8. Carbon, 8. Oxygen, 8. So this is indeed the Lewis structure for carbon dioxide. Okay? So we did examples of these 5 rules with 2 structures, water and carbon dioxide. In our next video, we'll talk about exceptions to the Octet rule and writing more Lewis structures.